All right, and we should be going now. And so today I'll be talking to you about numerals and their alternatives in the Middle East and Europe. And I'll be doing so in relation to my new book, which is entitled Reckonings, Numerals, Cognition, and History. And I want to start with a reflection about the title. And I'll be reading a little section of the book, and then we'll get into a much more informal part of the talk. But really, I want to talk about why the book is called what it's called. And I'm drawing on and relying on the triple meaning of reckon. So first, to reckon is to calculate. In the modern world, calculating, working, and playing with numbers are far more important activities than in any earlier period. However, numeracy, or the quantitative counterpart of literacy, it's fundamental to the functioning of all large-scale societies, including pre-modern ones. And mostly today I'll be talking about pre-modern societies. Numeracy is central to trade, to the appropriation of wealth, to the redistribution of surpluses. And working with numbers at a smaller scale is part of all sorts of everyday practices, measuring out quantities for recipes, working out the number of days until the next season of your favorite show is released, tallying the number of guests at a party, back when we could have parties like that. So reckoning is a nearly universal social practice that has taken on new meanings and new functions in contemporary capitalist and industrialized societies. The mathematician John Allen Paulos correctly diagnoses, though, that despite the ubiquitous nature of arithmetic in modern lives, people don't always have the tools needed to adequately work with numbers. And sometimes this can lead to enormous feelings of inadequacy. And as a response, some people actually take a perverse pride in their innumeracy in a way that we would never do with illiteracy. But reckoning, counting and calculating, I want to keep a suitable semantic distance from words like mathematics. You do not need any mathematics whatsoever to understand my talk today. Understanding how people, past and present, reckon, how they work with numbers, helps us grapple with their life ways. Those of us who learned arithmetic using pen and paper, working with 10 digits and place value, may find it natural, or we may take it for granted that that's just the way it's always been done, or at least that's the way it ought to be done. But think about the amount of time in the early school years that's spent just to teach place value, and you'll realize that this sort of numeracy is not preordained. And that's not even considering that pen and paper arithmetic requires the widespread availability of things like pens and paper. We shouldn't take that for granted. So over the past 5,000 years or more than 100 structurally distinct ways of writing numbers have been developed and used by numerate societies. And in my earlier book, Numerical Notation, A Comparative History, I spent some time talking about that. And there are thousands more ways of speaking numbers or manipulating physical objects or using human bodies to enumerate. And each of us is only familiar with a tiny fraction of the diversity of the world's systems for reckoning. And so the current universality of a particular set of those practices among Western, educated, industrial, rich, and democratic, or weird societies leaves much of the human condition uninvestigated. Second, to reckon is to think. The etymological and semantic linkage between thinking and calculation is strong in English, as it is throughout much of the Indo-European language family. We draw semantically on the mental activity of computation, and we extend it metaphorically to thinking in general. A reckoning is an estimation or a judgment that is undergirded by the mental work that's necessary to reach it. And so explaining the history of number systems requires that we understand the mental, verbal, and symbolic manipulations of mathematical cognition. And these cognitive operations are then embodied through language and gesture, and they're materialized through artifacts and notations. So numeracy is not just a social process, but also a cognitive one. But again, you don't need to be a cognitive scientist to understand my argument today. And that's because historical and cognitive disciplines in the framework I'm using work in parallel rather than in opposition to one another. And I want to include my fellow cognitive anthropologists in this discussion, many of whom have undertaken vital empirical studies of mathematics in the lives of daily lives of people. But I also draw on traditions such as the historian of science, Sir Geoffrey Lloyd, or the classicist Jocelyn Penny Small, that these are analyses that use fragments of historical and linguistic and archaeological material to talk about cognition across long periods, in light of the impossibility of direct experiment or observation. Finally, building on these first two reckonings, to reckon is to evaluate, to assess, to assign worth, to judge. We make choices and judgments that have consequences. When it comes to number systems, the prototypical instance of this tension, one that I'm going to talk about today, is the replacement of the Roman numerals for most purposes in Western societies. The traditional narrative holds that late medieval and early modern people evaluated those two systems, chose the more efficient one, and abandoned the more cumbersome Roman numerals. In the Arabic script tradition, which I'll also talk about today, the replacement of the older ABJAD numerals using the signs of the script with the 10 positional digits is seen to reflect that same process. I'm going to acknowledge that people make decisions and that those decisions have reasons that make sense to them. And if that weren't possible, if it weren't possible to make sense of what people's decisions were, then a cognitive and comparative analysis of numeracy would not be possible. But understanding how people's decision-making works is not simply a matter of efficiency. The reasoning that we might use to make some judgment need not be universal. And in fact, universal principles of rationality are very unlikely to provide a full explanation for what we're observing. Figuring out how and why people choose one way of doing things and abandon another is not trivial. In dealing with the reckonings of users about which numeral system to prefer, we have to be thus careful not to assume a universal logic or particular outcome. People are not rational choice machines, and we need to understand their cultural rationality. Now, this is particularly important when we're looking at people far removed from the context with which we're familiar. We want to understand the long-term processes by which the reckonings of individuals at discrete periods come together to shape the histories of numerical systems, until they too inevitably meet their day of reckoning. Not only are we not at the end of history of numeration, but there can be no such end as long as humans are still judging and evaluating their numerical tools. Numerals, cognition, and history. These three reckonings are the three central themes of my book. Each element of this triad is essential for understanding human numbering practices and the social context of written numbers, or so I reckon. All right, moving along. Just a brief note on names. Here are three number systems, some of which may be familiar to you. And if we were to look in the literature, these go by a huge variety of names. So for instance, you might see the system up at the top called the Arabic or the Indo-Arabic or the Hindu-Arabic system. You might look at the second system. It can also be called the Arabic system or the Eastern Arabic system or the Hindu system or Akam Hindiya. Or you could look at the third system and it could be called Indian or Hindu or Devanagari. As you can see immediately from this, we're going to have some terminological difficulties. I want to clear the deck, so to speak, and replace those with a simpler system that is much clearer what I'm talking about. And in place of what we often call the Arabic numerals, I want to simply call these the Western numerals. Now, in saying this, I want to be very clear. I don't mean to deny that the Western numerals are descended from an Arabic ancestor and ultimately from an Indian ancestor. These are all modern cousins of each other. They're all descended from a system developed in early medieval India and then which is now spread to become global. And of course, there are many other systems. There are in fact dozens and dozens and dozens of systems that are all base 10 positional systems. But I want to acknowledge that by calling this the Western numerals, I don't mean to assume their universality. In fact, quite the opposite. I want to acknowledge that this is the system that developed in the West out of another ancestor, but that has its own symbols, its own practices, its own meanings, and that those really became fundamental to, in the period from around 1500 to the present day in Europe and in the Americas. And so that's a terminological distinction I wanted to make just in case there was any confusion about what I'm talking about when I talk about these Western numerals. These are the numerals that are most commonly encountered globally, but are quite distinct, of course, from the numerals used alongside the Arabic script, which I will simply call the Arabic numerals. All right. Now, we know that writing numbers is a ubiquitous phenomenon in almost any contemporary human environment. In fact, you could take a moment to look around the room where you're sitting. They're everywhere. Perhaps stamped underneath your comfortable chair, a serial number. Around your wrist, a number telling you how many steps you've taken today. Inside a wedding ring, a carat mark, 22. On a TV, a batting average, a box score, the top of the seventh with your team 1 run down. In the metro station, the numbers 1 through 12 on a clock telling you just missed the last train. For the most part, we don't think deeply about these numbers, even though it's certain that people in the industrialized world encounter hundreds of them every single day. They linger below awareness. But now I want you to think about each of these numbers not as some random feature of your landscape, but as an intentionally created communicative product, a product created by a literate and numerate mind. Now, perhaps not with you specifically in mind, but with some audience in mind. In other words, numerals are principally for communication, not for calculation. I want you to think thus about written numbers as texts. How were these numbers chosen? Why those ones and not others? Why does your credit card have 16 rather than some other number of digits? Why do we separate every third digit of a number greater than 1,000 with a comma? And why don't we do that to the right of the decimal point? Why are there Roman numerals numbering the pages of the front matter of the books we read? And why, after all, don't we use the Roman numerals much anymore? Now, in other work, I've described a typology for number systems. I'm not going to spend a great deal of time on this today, but I wanted to present it to you. One of the things that's really important to know about numbers is that all number systems, all of the 100 or so number systems that have been studied, really fall into one of 5 basic types. There's all kinds of variation and interesting quirks and historical features of these systems, but they can all be subsumed under one of these 5 basic categories. I think this does tell us something fundamental about the way that numbering works, because these aren't derived in a simple way from language, that we know that in fact, these aren't purely linguistic phenomena. They're semiotic or communicative phenomena that don't derive directly from language. Rather, they're a notation system and that they have a structure. So it is really important to note that numerals are ordered and structured. So in part, this is the source of, I think, many of our intuitions that probably if one system is replaced by another, then it must have something to do with their structure. And without denying that that's part of the answer, I think we've stressed that, and the literature stresses that to such a degree that I want to present an alternative scenario. A scenario where structure is relevant, but only to a degree, and that the decisions that humans are making are much more complex. So to answer the question of why we don't use Roman numerals anymore, you need something more than simply looking at them and saying, well, that's what they're like, and that's why people abandoned them. It's really important to note that the Roman numerals were nearly ubiquitous throughout Western Europe from the 3rd century BCE to the 15th century CE. In other words, they fell out of use commonly in the early modern period, retained for prestige or archaic functions, or when a second set of numerals is useful. And if I were to ask you why, as I've asked hundreds of people over the years, you might say something like, have you ever tried to multiply with those things? And then that's an understandable response. Many of us may have a memory of being taught Roman numerals in school and being given artificial puzzles like DC XXXX VII minus XCIII. This is a minor form of torture, perhaps. Roman numerals, to the mind trained in modern Western arithmetic, may seem obscure, awkward, or too long to be of use. But not only do we not do arithmetic with Roman numerals, neither did the Romans or the medieval inheritors of their notation. They used an abacus or counting board, or they used the fingers, or they used mental calculation. They used written numbers only for representation. A better approach to this question would ask about the choices and motivations of writers and their audiences in relation to the text themselves within specific social contexts. Whether we write 637 or DCXXX or Execosia Triantaeta is not just a matter of what language we speak, but what audiences we imagine ourselves to be addressing and what impact we want to have on them. So, why don't we use Roman numerals anymore? So, because the answers I've been given echo this single theme of computational efficiency, the idea that the cumbersome Roman numerals were unable to compete and so they faded out of use, doesn't seem to me to be adequately empirically investigated or justified. So how would we know? How could we establish under what circumstances the users of the Roman numerals, or in fact any number system, shift from one notation to another? We know it happened. But to ask to argue that it's a case of efficiency requires that we ask, what does efficiency mean? And I think the Roman numerals are an interesting case study because they're surely the best attested case of a once popular notation that fell out of everyday use. They were adopted early, used by the extremely powerful, and in fact replaced by the extremely powerful. Their replacement wasn't a matter of colonialism or anything like that. So in order to establish what the representational effects of numerical systems are and whether they motivated this change, we need to address these four questions. First of all, what are those effects? Are there actual effects that provide real cognitive advantages? Second, were those advantages relevant to the tasks and contexts for which these numerals were used in a specific society? Third, were the notation's users aware of these advantages, and did they perceive them as being relevant to their needs? And finally, were those advantages effective in producing a transformation or replacement of a numerical system? So in Reckonings, I take this framework and apply it at great length, and I'm not going to do so today. But I'm going to point out that we need to be able to answer yes to these sorts of questions. I'm going to focus to some degree on the third of these questions, because I think one of the things that really becomes apparent when you look at the historical record is that people didn't feel that the systems they were using were so bad. They felt differently than I might feel or that you might feel about whether these systems are really so terrible. So let's talk for a second about the Roman numerals. We may think we all know what these Roman numerals are, from m equals 1000 down by 5s and 10s down to I equals 1. And of course, that's what they look like today. But if we were to look at them during the Roman period, they would actually look quite different. So here's a Roman inscription. It's a tablet from the 1st century CE. And the first two lines are mostly made up of Roman numerals. And those strange lines at the top, the curves, actually are numbers for 10,000 and 5,000. Those little things that look like an infinity symbol are actually a sign for 1,000. So this is an amount of 38,079 sesterces. And I think for most of us, unless we're really well trained in reading Latin paleography, that doesn't look like 38,079 in Roman numerals. So it's really important to know that even what we think the Roman numerals are requires that we take account of the fact that they weren't originally letters at all. They were originally abstract symbols that only later became accommodated to the letters of the Roman alphabet. That they don't actually have an alphabetic origin will actually become relevant when we come to think about why they're used in the way they're used. And so we see that the Roman numerals were essentially the instruments of power in the Roman Empire, and they became used in great inscriptional context. Here we see the columna rostrata in honor of Gaius Duilius, victor in the First Punic War, an inscription with at least 22, but there's of course many signs missing from this fragmentary inscription. Probably as many as 32 signs for 100,000, repeated one after another, after another, after another. And this is pretty impressive. And so one of the reasons I think that Roman numerals are really valuable to people is actually not that they're short, but that they can be long. Their length can in fact be an extraordinarily valuable thing if you're a writer seeking to communicate the magnitude of an amount of booty taken in the aftermath of a battle. And this is a phenomenon that I've called conspicuous computation, and that I write about in the book and write about elsewhere. So the Roman numerals were really central to understanding Roman power, and they were the numerical system used in Roman and then post-Roman writing for a very, very long time. So the Western numerals, in contrast, come in a very sort of humble way. This is a fragment of a text called the Codex Vigilanus. It's a 10th century text written in Spain. And it's one of the first pieces of evidence we have that the Western numerals were starting to exist as a thing separately from the Arabic numerals. In other words, this is knowledge that's coming really from three sources. It's coming from up north from what's now Morocco into Spain. It's coming from Sicily and the Muslim occupied islands in the Mediterranean up into Italy. And it's coming through Byzantium into the east. And so this is a text that basically presents the numbers 1 through 9 in a way that some of them are probably familiar to us. But of course, there's a lot of development still to go on here. This is pretty early. And in fact, mostly after these sorts of early texts, you don't have a great deal of evidence for Western numerals in European texts throughout the 10th, 11th, and 12th centuries. Things start to change a little bit with the writing of the Liber Abaci of Leonardo of Pisa, who's also known as Fibonacci, of the famous Fibonacci sequence. The Liber Abaci, despite its name, is not really a book about the abacus at all. It's really the first systematic account of how one could use Western numerals in arithmetic. In other words, a technique known as algorithmus. It's really the first systematic account that was widely taken up. It is not the first account, but it's the first one that really gets taken up and starts to become used and adopted more widely. But I want to stop here and just recognize that just because somebody wrote a book doesn't mean that all the other ways and older notation stopped. And in fact, there's lots and lots of manuscript evidence for the use of Roman numerals. For instance, this is a multiplication table where you could basically see the numbers 1 through 10 multiplied by 1 through 10. This is a very interesting text. This is actually a very simple one. Roman numerals were used in this sort of context for arithmetic. But note that when I say for arithmetic, I don't mean that Roman numerals were lined up in columns or anything like that. Instead, they were used as representations. The reader of this text would then do calculations in some other way on an abacus or on the fingers. But Roman numerals were not seen as bad for arithmetic or useless for that purpose. Far from it. In fact, the replacement was extremely slow. So here I'm going to show you a bit of a text. You don't need to be able to read all of the Latin. This is the Opusculum of De Santo Marco, printed by Richard Pinson in London in 1505. So this is about 50 years after the development of the printing press. And this is a really early example of the use of Western numerals in print. But I'm going to show you, you can see here, there's this number. This is the number 1505. The problem was, and this was a problem for many early typesetters, that if you didn't have in your typeset a set of Western numerals, you had to find some way to do it. You had to find some way to account for it. So those little things that look like squiggly H's, those are H's. It seems that Pinson thought that H looked enough like a 5 that it could be adopted for that purpose. But one has to ask the question, did the reader of this text understand that it was a 5? How was it understood? In fact, they probably did, but only through context. Because if it's 1505, maybe you're looking for text that maybe says 1505 in it, but it doesn't look like anything like the way that a 5 would have been written in a manuscript at the time. And we see at the same point that this book is paginated or foliated entirely in Roman numerals. And in fact, what's really interesting is when you look at texts of this period, it's really striking. You can find books that have all of the pages numbered in Roman numerals, and then you go to the index, and the index is all in Western numerals. You can find other books that are the other way around. All the page numbers in the pages themselves are in Western numerals, but the index is all in Roman numerals. So there's this sort of very, very fluid period in the 14th, really in the 15th and 16th centuries, where some sort of transition is ongoing. Now, I want to stress that during this time, basically nobody ever complained about the Roman numerals. It's really, really hard to find anyone who says, yeah, I'm abandoning these because they're no good. And this contrasts greatly with the way that modern historians of mathematics have dealt with it. So here, Eric Temple Bell, in his text, The Development of Mathematics, called the Roman mind crass. The cumbersome Roman numerals can be called a mathematical creation only by undiscriminating charity. This is probably the worst example I can find, but it's not the only one. The medievalist Alexander Murray similarly argues that the Roman numerals put an absolute limit on learned arithmetic, and that it was essentially a flaw in notation that crippled numerical exploration. Other examples like these from the 20th and 21st century literature abound. And there are things in the medieval and early modern record that look a little bit like this, but when we look at them a little closer, we see that they're not. So here is a woodcut from the Typus Arithmeticae of Gregor Reich, published in 1503. In other words, just 2 years before that text from Pinson that we saw, printed by Pinson that we just saw. And here we see it's a sort of an allegory. On the left is Boethius using the Western numerals with pen, writing down numbers and something that looks like some kind of modern arithmetic. On the right is Pythagoras. Pythagoras is using reckoning on the counting board. And in a nod in the allegorical tradition of that period, arithmetic, who's the female figure in the center, has Western numerals bedecking her gown and is turned towards Boethius in recognition of his superiority. But note what this is not, and note what this is missing. There are no Roman numerals on this text. This isn't a comparison of Roman numerals and Western numerals at all. It's a comparison of two forms of reckoning or calculation, but it's not a comparison of two forms of notation. There are no Roman numerals in this woodcut. The Roman numerals were simply not relevant to the kinds of evaluations that this allegory represents. Now, a bit later, say by the early 1700s, you do start to see these. So for instance, here you have John Arbuthnot, who in his essay on the usefulness of mathematical learning talks about how glad he is that the Roman numerals have been abandoned and how much that it's benefited civilization that we have stopped being barbarous as, quote, some Americans, by which he means Native Americans, who can hardly reckon above 20. And we see in this sort of early sort of Enlightenment thought much of the kind of racism and the ethnocentrism that really characterizes many of the texts of this period. But this is really quite late. By 1701, the Roman numerals are already gone. This is the whole point that Arbuthnot is writing. He's glad that they're gone. And so rather than seeing this as what motivated the change, we ought to see this as an after-the-fact justification made by a writer living decades or in fact centuries after the change had largely occurred. And in fact, when you look at how Roman numerals are described in books, the description of Roman numerals as cumbersome or clumsy or awkward is in fact a product of largely of late 19th and 20th century thought. So this is some data from the Google Ngram viewer, which basically shows the word frequency of things like cumbersome, clumsy, and awkward relative to the phrase Roman numerals. So how often are those adjectives used to describe them? You can actually see that the spike really only starts in 1900, and there's this period in the mid-20th century. I actually think this is the period where students were most likely to be tormented by their teachers to learn the Roman numerals. And it would be understandable that if that was your impression of them, that this would be how you would view the system, as cumbersome or clumsy or awkward. But people in early modern and medieval Europe certainly did not seem to regard them in that way. The change happened, but it happened for different reasons. In fact, the reason I set out in the text is that with the invention of the printing press, once the printing press does develop, you do have the potential to see written arithmetic texts that become available to a much wider set of users. So pen and paper arithmetic really is scaffolded upon the edifice of printed arithmetic. And that produces a new set of literate users. And they were at that point free to choose a new form of reckoning, of calculation. And that this then in turn led to the adoption of Western numerals more broadly. But rather than see the mathematical origins in the Liber Abaci 300 years before the transition happened, think about how something that takes 300 or 500 or 700 years to be replaced, this is not being replaced because everybody immediately saw it was better. Far from it. But of course, even when we say that the Roman numerals were replaced, what do we mean by that? The Roman numerals are still used very widely, whether it's on Justin Bieber's right bicep or advertising for the Super Bowl or on a pocket watch. Those are places where we might see them occupying a prestige function. But we also use Roman numerals, of course, whenever we need a secondary notation in the prefatory material of a book or to indicate chord changes. It's actually really useful to have a secondary notation. The Roman numerals haven't disappeared. They probably never will. This matter came to the head in 2020 when Elon Musk and his partner Grimes had a baby, and they decided to give it the name X-A12. Now, little X-A12, we can debate the merits of that name. We can debate whether that's a good name or not. That's not my point. But the real challenge came with the laws of the state of California, which prohibit any non-alphabetic characters to be used on birth certificates. So in fact, the name X-A12 was unacceptable. So they had to first change that ash, that combined AE, into two separate letters, AE. But more importantly for our purposes, that they were able to change the Western numeral 12 into the Roman numeral 12. And so little X-A12 still exists, but with the name X-A-XII. And that was permitted because under the reckoning of the state of California, the Roman numerals are letters. This takes us all the way back to the beginning in the transition of those abstract signs, those abstract numerical signs into the letters of the Roman alphabet, allowing this transition to have happened. The Roman numerals are still alive and well if we look at the way that they're actually used. Now, I'd like to turn now to talk for a bit about Middle Eastern number systems and to talk about the same sorts of processes that are ongoing in Middle Eastern societies very, very broadly. And one system I want to introduce you to, and some of you may know this system, but I know many of you will not, are what are the ABJAD numerals or the AL-JUMMAL. And this is a non-positional system, which is what's called a ciphered additive system. In other words, there's one sign for each multiple of each power of 10. There's a separate sign for each of 1 through 9, 10 through 90, 100 through 900, and 1,000. And so you don't need a 0 to write 642. You simply write the sign for 600, followed by the sign for 40, followed by the sign for 2. And these are following a set order. In other words, they're following like an alphabetic order because these are signs of the Arabic script, the ABJAD. Now, alphabetic number systems in general, systems that rely on the letters of a script in order, are actually really common in the Middle East, but actually throughout Europe and North Africa. So for instance, there are parallel systems in Greek, in Hebrew, in Syriac, in Ethiopic, in Coptic. There are many, many of these alphabetic systems, of which the ABJAD numerals are only one. This particular system seems to have been developed around the 7th century CE. It's probably an Umayyad development. It may be a little bit earlier. The pre-Islamic evidence is a little complex, and so I won't get into that today, but simply to know that this is a system with a very, very long history, going all the way back essentially to the origins of the Arabic script as a distinct script tradition. The ABJAD numerals, like the Roman numerals, were widely used in science for representational functions. So especially in astronomy, but in all sorts of mathematical texts, ABJAD numerals throughout medieval Islamic world are extraordinarily common. And so we tend to think, again, of the replacement of these older systems by positional numerals as a very quick, very rapid or obvious process, but it simply wasn't the case. Having said that, it is very clear that very, very early on, people in the Middle East were starting to become aware of the developments that had been going on in India. One of the earliest such figures is a Syrian bishop, Severus Sebald. This text is probably written around the end of his life, so I think it's around 662 CE. And here he praises this science of the Hindus, which he doesn't spend a lot of time on, so he says he's going to omit it. But he feels that it's really important to talk about how this computation is done, just only to say that it's done by means of 9 signs. He, again, doesn't mention the 0. Probably the reason for this is actually that 0 wasn't seen as a separate numeral sign. It was seen as something else, as a placeholder or some other sort of thing other than a number sign. This is an interesting discussion that I'd be happy to elaborate on later. But he's very clearly enthusiastic about the new system. But despite this description, it is not the case that Indian development of place value and positional numeration is common in the 7th or 8th centuries. In fact, even in the 10th century, there are other forms that are preferred. So for instance, here we have a passage from Muhammad ibn Yahya al-Suli in his Adab al-Kutab 10th century text. And he does talk about Indian numeration, and he basically says that the scribes refrain from using these numerals because they require the use of materials. In other words, the ideology of this system was that writing things on paper was really quite crass, and that it wasn't good for ensuring secrecy, and it wasn't good for keeping with dignity. And so instead, reckoning with the fingers was what was recommended. You could use numbers to write down, a result, but the calculation of the result ought properly to be done with the fingers. And so you can see that something that we wouldn't necessarily think, we would think that it would just be obvious that once you have base 10 positional numbers that everyone is going to adopt it. But this simply wasn't the case. In the same century, and really around the same time, Al-Uqlidisi presented was really the first full accounting of what he's called the HVSAB al-Hindi, the Hindi numerals or the Hindu numerals. And here he notes that it is easy and quick and it needs little precaution. And when he's talking about computers, he's not, of course, not talking about an electronic computer. He's talking about a reckoner, somebody who's calculating. And he points out that it has an advantage, which is that if you start writing something down and you get busy, you come back to it, it's still the same, and you can continue on doing it. Thus, you don't have to memorize it. But note that that's actually true of any number system that you might want to use. It's not really talking about lining up numbers, or it's not talking about the value of place value, or that you can extend numerals infinitely. The value for him is, yeah, compared to, working on the fingers, it's really convenient to write your numbers down so that you don't make a stupid mistake. But in fact, he goes further because he points out that at this point, other people disliked it. So he's really talking here about the takht, which is a dust board. But essentially what a dust board is, it's a tablet on which you spread some dust and then you write calculations with your fingers in the dust. And so basically we're in sand. And so he points out that some people think it's ugly, or to say that, well, I don't like that. But he says, well, instead of using dust, why not use paper? But then note what he says at the end. We may hide it also by means we shall mention, so that one who sees him that computes with it does not know that it is Hindi, but thinks that it is Rumi. Well, what does this mean? What is Hindi and what is Rumi? What he actually means by this is, well, maybe you don't want to tell everybody that you're using this new Indian calculation. Maybe you actually want to make it seem like you're doing something else. So maybe you'll use this Rumi. Well, what is Rumi? Well, Rumi is Roman. He doesn't actually mean Roman numerals, though. He actually means by Roman, he means Greek, i.e. Byzantine. So in other words, the idea was, instead of using these Indian numbers when you write them down, use some Greek numbers, or in fact, use ABJAD numerals, which are sort of seen as having that same Greek ancestry. So in fact, many texts from this period don't actually contain Indian numerals or Arabic numerals at all. We know they were used because we have this textual evidence that they were used, but the texts themselves don't contain them. They were perhaps used on the dust board and then effaced, thus hiding any evidence that they were ever used at all. However, I want to point out that even despite this, the ABJAD numerals, the older system, survived a very long time. Here we see a Persian astrolabe from the 18th century. In fact, and there are 19th century examples as well. Astrolabes are extraordinarily complex instruments for manipulating numbers and manipulating knowledge of the heavens. And you can see actually at the left, you can see these are actually along the edge, interspersed with little circles, which are kind of indicating in between each decade are the numbers 30, 40, 50, 60, 70, 80, 90, 100, working from top down to bottom. So why are these extraordinarily mathematically capable astronomers and mathematicians in the 18th and 19th century using ABJAD numerals on text like this, or on artifacts like this? Well, one reason is that they're shorter. Unlike Western or Arabic numerals where you need signs for zeros, these signs don't require a zero. And so it's actually really convenient and concise to be able to write in these really very small artifacts, to be able to inscribe these numerals. One of the real advantages of these sorts of ciphered additive systems, like the ABJAD numerals or the Greek alphabetic numerals or the Hebrew numerals, is that wherever our numbers, where any of our systems would require a zero, basically it can be expressed more concisely. And so I think the conciseness explains part of it. But part of it is also that this is a continuity of a centuries-long tradition. This is 1,000 years or more after Indian numeration was introduced into the Islamic world, after Arabic numerals started to be used. And 1,000 years later, they're still being used, in a very, very scientifically advanced purpose. But it's not just that old systems were retained, new systems were developed. Here we see the Siak numerals, and Siak numerals go by different names in different traditions in the Middle East, Siak or Diwani or Rokum, and these are things like, are almost just called like the writing or the recording or the arithmetic. This is almost like a way of understanding these terms. And these are completely different than the ABJAD numerals or than the Arabic numerals. This is basically a system that's actually used in commercial recording and in writing contracts, especially in the Ottoman period. There are early examples from sort of medieval Islam and the medieval Middle East, from medieval India, but mostly these are sort of Ottoman and on 14th, 15th, And then right up until the 20th century, these were still being taught and used in schools in places in Persia, for instance. What's really interesting about these is that their origin is not in some other number system or some other notation, but these are actually really contracted versions of words. These are really contracted versions of Arabic words for the most part. And basically they're contracted to the point where I don't think that even Arabic speakers can look at most of these and say, oh, I can read that word. That's definitely the word I'm looking at. In fact, the purpose of the SIAC numerals is actually cryptographic. The purpose is to not be understood. The purpose is to hide what you're doing. And we can understand for commercial reckoners, that actually serves a lot of value to not be showing the mysteries of your craft, to not show every piece of the calculation you're doing is sometimes the value. Yet another Ottoman cryptographic system is used, and we see it here below, and this is a much rarer system than the SIAC, but it's this system you see at the bottom that have these little things that look like flowers or plants or things like this. But there are a variety of these systems that were used in the Ottoman military and used in manuscript traditions. This is from 1262 AH, which is 1846 CE. That these are new systems that are being developed. And these are not positional base 10 systems really at all. These are more like those ciphered additive systems I was talking about earlier. But they use a variety of notations. And in fact, it's the number of branches on each side of the leaf that expresses various numbers from 1 through 9, 10 through 90, 100 through 900, and 1000 through 9000. So in summary, these non-place value systems persist for a long, long time after the introduction of the purportedly killer positional decimal systems. That not only do they persist, but new ones are developed. And that Roman numerals and ABJAD numerals are not simply things that are retained for prestige or symbolic functions, for numbering kings and popes and Super Bowls, but for actually very practical and in fact, very scientific ones. This actually tells us something, that efficiency for calculation wasn't really a motivating factor, wasn't the main motivating factor in what was going on here. I'm not going to deny that for some people that may have motivated them. Clearly it did. But in fact, what we see is that the retention of the old and the development of the new actually has some other set of explanation other than one simply relying on cognitive efficiency. Bearing in mind throughout all of this, that in fact, reckoning on an abacus or counting board or with the fingers was actually seen as more valuable, as more useful for many, many of these speakers. To wrap up in very, very notoriously weird fashion, what is the future of numerals? Are we, in decades or centuries to come, going to be using Klingon numerals on our clocks, as we see here? You can buy this Klingon numeral clock, by the way. Someone will sell this to you. I don't think that's true. But the real question is, have we reached the end of history of numerals? The historian of mathematics and popularizer Georges Ifra certainly thinks so. He thinks that our positional number system is perfect and complete. It's as economical in symbols as can be and can represent any number, however large. And he concludes that once it was achieved, no further discoveries remain to be made in this domain. Well, we've seen that that's simply not true. We've seen that there really are discoveries that continue to be made. In fact, I'm going to tell you that sitting right now, probably in your pocket or maybe on the desk beside you, there is a number system developed in the 20th century that's different than any of these number systems. In fact, there are hundreds of examples of this in your own home right now. And that's the system of numbers that are used on resistors, that are used in electronics. So these are color bars that resistors are little small pieces of everything from your cell phone to your computer to your television. Literally, there are hundreds of them in your home. And resistors generally have a notation in terms of a series of small painted bands of various colors, each of which has a meaning. And so here we see a 680 ohm resistor with the blue meaning 6 and the gray meaning 8 and the brown meaning 1. So in fact, what this is the first two numbers tell you are a positional notation system. They use place value along with colors for 1 through 9 to indicate various numbers, in this case 68. But there's no 0 in this system, but rather the third bar indicates the power of 10. In this case, brown means 1, which means 10 to the power of 1, or 10. So this is 681, 68 times 10, 680 ohms. If it was 180 ohms, we'd put the brown instead of the blue, 181, 18 times 10, 180 ohms. Or maybe it was just 600 ohms. Well, now you only need 2 bars. Blue, red. Blue means 6, red means 2. Now we know it's 6 times 10 to the 2, 600 ohms. This is a new system developed to serve the needs of reckoners, real calculators, human beings in the 20th century. These don't exist for the computer's sake. They exist for the person who works with these, who puts together chipboards, or who repairs chips, and who works with computer boards. That the value of these is that they're easily visible and they're easy to depict rather than trying to write small numbers on a resistor. They're easy to see, and it's very easy to see by looking at that third or the rightmost bar. We'll ignore the gold bar, that's a separate thing. To see approximately approximately what the resistance is. You can see that very, very easily by just saying, it's brown. It's going to be somewhere, something times 10. Or, oh, it's red. Oh, that's something times 100. Or if it were blue at the end, it would be something times 1,000,000. I don't think there are too many million ohm resistors, but I'm sure they exist out there. This is a new system. New numerical innovation continues. In conclusion, the history of numerals thus is not a unilinear progression from bad to good leading up to the present day. Both the Middle Eastern and European cases show complex processes of replacement and retention. And honestly, because numerals are not for arithmetic, because we mostly don't use them in the way that we imagine that they're evaluated, people simply aren't evaluating whether these are good to be lined up in a particular way. In fact, we need to understand how and why people make choices between alternatives. And that's as true in the Middle East as it is in Europe, as it is in the present day. In other words, we are not at the end of history of numeration, and I don't think we ever will be. Thank you very much. I'd be happy to take any questions.
Thank you very much, Steve. That was excellent. There's some good comments that are coming in. I invite everyone to go ahead and write your comments if you want, but also raise your hand, and I will invite you to unmute yourselves, and you can ask your question directly of Steve. Let me go ahead and take this chair's prerogative and make the first sort of question comment. Now, I happen to be very lucky. I've read the book, so I've seen a lot more of all of the kind of detail that goes into this argument. And this last point you make about the future of numeration systems and the past really does seem to be quite central, a central point in your book. How do you know what happened in the past? Can you look at the present to tell you something about the past? Can you look at the past to tell you something about the present? I think that's quite interesting. And then when you do what you do near the end, where you sort of look to the future, can you look at numbering systems today to see what the future will be? And the one that caught my eye was actually the base 4 DNA system that you mentioned as I think you don't say it's going to be the future of numbering system. You say it to flummox us, to say numbers can be all kinds of things. So I'm wondering, when you say that Europeans struggled to understand that zero, and they struggled between the 7th and the 11th centuries because they couldn't understand the concept, I wonder if you might just comment about how much we would be struggling to understand the concept of a base 4, or you've just given us the resistor example. What is it there that we're not getting? What's the mindset of the ohmed resistor numbers or the DNA CGDT numbering system?
So the first thing I'll say is that human beings are really rather clever. That was true in the past as it is today. It's not that these things are impossible to learn, But the most important thing is to think about what are the factors that might militate against the adoption of a system. If something is a little bit hard, because humans are relatively lazy, sometimes we're happy with something that may not serve all of our needs if it serves some of our needs relatively well. So it's not simply that one can't understand a system, but it's, well, is this really worth me changing? What would make it worth me changing to some other system? And that barrier, and so there's an argument really from evolutionary anthropology that I raise in the book about what are the sorts of things that lead you to suffer that barrier. But you sort of see the same phenomenon, for instance, the fact that we use QWERTY typewriters as opposed to some other keyboard layout that might be in some sense more efficient. Dvorak keyboards have their advocates where the letters that are most common are much closer to where the index and middle fingers are, rather than having F's and J's there, which are not so common in English or in fact in many Western languages as compared to E's and T's and S's. But for the most part, we all learned to type in a particular keyboard and the cost of learning is too high. So rather than think about like, oh, why are these systems so impossibly complex to understand? I really want to refocus your question and really ask, what makes us see, oh yeah, that's kind of neat, but is it really worth changing? Does it really make it worth my while to change? I also want to bear in mind that if you take that numbers are representation systems, not just systems for doing your own reckoning, for doing your own arithmetic, there's always the question of who is my audience? Do they understand the numbers I'm using? So when I choose to use a different number system, one that isn't well understood, the problem may be, it may be more efficient according to some factor that one could choose. But in fact, the real problem is nobody understands what I'm talking about. And so if my goal is to be understood, which it's not always, we saw those cryptographic systems, but if the goal is to be understood, then part of the calculus of what's going to motivate that change is going to be, who do I want to communicate with and what range of users are already using this system? That's actually going to be one of the main limiting factors. In fact, I think that's one of the most important reasons why the Roman numerals were retained as long as they were, because this new system was a novelty and it had to overcome the fact that it was rare and thus not as good for representing and communicating as a system that was broadly understood.
Thank you. We've got Tony Christie who'd like to make a comment. So Tony, I've just invited you to unmute yourself.
I want to comment on retention of number systems and also a peculiar number system, which I recently learned about. I worked with Schmiedel, who's a historian of Arabic science, and she's translating and annotating a 13th century Yemeni text on astronomy and astrology. And I copied her English. And the last two chapters of this, we're not doing it sequentially, are about number systems. The last one is about the Hindu number system, but the one before has a thing which is called the astronomer's arithmetic. And the numbers on the whole number side of the decimal point value system, on the fracture side of the decimal side, they're in a sexagesimal number system, and all of the numbers are written in ABJAD numerals.
Correct.
Which is kind of bizarre.
No, it's not bizarre at all. In fact, this is actually quite common. Astronomers were particularly persistent in holding on to those ciphered additive systems. Not just Arabic astronomers, but also Greek and Syriac astronomers and Hebrew astronomers. And so these sorts of astronomical fraction systems that use a ciphered additive system without a zero, along with, I talk about this in my previous book. I do not talk about it in Reckonings, but this is a way in which it's unlike where we use a base 10 system to represent time in a base 60 system. These are actual sexagesimal numerals. They're base 60 in a very real way. And so astronomical fractions are a really striking phenomenon. And they basically exist because once you've divided up the circle into 360 degrees, it's very, very useful to have a base 60 numeral system because the divisors, there are so many divisors. 360 is what's called a highly composite number. In other words, it has a lot of divisors relative to numbers below it, in fact, above it. That is a technical mathematical definition, which I won't get into. But yes, absolutely. So these systems persist, and I didn't really get into it, but this is actually part of what's going on with these astrolabes, is that these are really useful because dividing up things into 360 is of course the way that you need to be able to do things. So 60s and 360s are fundamental to doing astronomy up to the present day. The difference is that in Europe, largely outside of Greece, that notation was never used, or it was rapidly abandoned in favor of a straight decimal notation. But I do think that there really are some practical reasons why sexagesimal fractions were used to represent, they're really representing fractions of the circle, in other words, degrees and minutes on the circle. So that's a short answer to something that I outlined in my previous book, Numerical Notation, in some greater detail. But thank you so much for your question.
Okay, thank you. Now, Anton Totner has a question. I've just invited him to unmute.
Yeah, thank you very much. I have to admit that my question is quite specific. I'm a historian at Vienna University in Austria, and my main focus is in early modern history and on the use of numbers to identify subjects or objects. Mm-hmm. So not to count, not to order things, but to identify, for example, house numbers, about which I've worked a lot, but also like policemen or people who are in jail, and so all this kind of use of nominal use of numbers. And I would be interested if in the notation systems you have studied, when numbers were used to identify things, objects, or whatever. And maybe, because as far as I know, in Greek antiquity, the letters that were also used as number signs, they sometimes were used to identify objects, but in Roman antiquity, this was perhaps not so often the case. And maybe this could be also a kind of reason, or why other systems of notation were perhaps then preferred to the Roman system, but that's just a speculation of me. But I would really be interested in this use of numbers to identify things or people or subjects.
Yes, thank you. And I should say that Dr. Tentner has a really fantastic article. I think it's just called Addressing Houses or something like that, from about 10 years ago or so on house numbering. And it's really interesting because actually the kind of use of numbers as names is not really widespread in sort of Western, in European thought. And there are two sorts of questions. The first is, do you have to have all the numbers in order? Because that's one sort of problem. If all the numbers have to be in order, then you can sort of see this as an ordinal list. Oh, well, there are 10 people and we're just going to name them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The Romans did this all the time. They named their kids Quintus and Sextus and so on as a sort of naming practice. But the kind of, for me, the more interesting question is, what if the numbers don't have to be in order? So for instance, we all know that, buses, for instance, just because there's a bus 42 in your city doesn't mean that there's a bus 41. So in a sense, this is what's called a nominal use of number. It's not ordinal. It's not saying that bus 42 is the 42nd bus. In fact, 42 is just a fairly arbitrary number. There is probably a system to it, but it doesn't imply that there is a list of 42 buses of which this one is the 42nd. And that's actually, I think that's actually pretty rare even in Greek. I don't think there's the idea that you're just kind of giving a random number to something, that the number is always either seen as a cardinal, as a count, or as an ordinal, as an ordering number. I'll have to think about that some more because I don't actually know the answer. And I'm not, I mean, there are some people who I know would probably know the answer better than I would, who are classicists. But the idea that one is sort of assigning an arbitrary number to something is actually quite modern, like naming your kid X-X12. I mean, this is you know, these are these are amusing, but actually I think it's quite serious, because as you know, of course, from your own work on house numbering, we actually don't assume. In fact, in most modern house numbering systems, these are not ordinal lists. They're sort of in order, but they skip all sorts of numbers, and there's all sorts of weirdness. And then you have a number, I'm number 22 and a half, but there's no number 10. And these are really interesting phenomenon, because it takes numbering outside of the idea of counting something and turns it into a labeling system. So of course, I know you know this very well from your own work, but for the audience, I wanted to give some clarity to that point.
Yes, I actually would be very much interested if there are other people working on this kind of topics. Yeah, thank you.
Thank you. Okay, Steve, we've got a question here in the chat that is quite near and dear to my heart. It's about Pakistani writing boards. So Khurshid Sana Khan says, it's interesting to know that Indians use dust boards for writing on. In Pakistan, small writing boards called takhti are still used. Could you tell us about the evolution of this takhti? Do you think that was from the takht?
Oh, yeah. I mean, I think it is absolutely from that. I'm not an expert on the sort of material culture of India or Pakistan. I don't want to speak out of my area of knowledge. But it's very clear that the use of boards is very widespread. And I think actually that, you know, it doesn't have to be a dust board, right? Like it really is in the case of what Al-Uqdisi is talking about. It clearly is a board with dust, because he's talking about, oh, you could do it, you could wipe it away, and you could do these things. It clearly is a dust board, but it can of course also be a board simply on which you write. Could be slate, or it could be a wooden board on which writing is done. There are a variety of media and means. So I don't mean to suggest that there's one sort of thing that is the top. And in fact, but more than that, I would be sort of outside of my direct area of knowledge, and I wouldn't want to speak beyond that. But it's very clear that tradition of writing on boards in the Islamic world is extraordinarily widespread.
Was that something that also happened in Europe?
So in Europe, the slate is more common, and of course there are slates going back to classical antiquity. There are also wax boards. So that's another very common in sort of classical antiquity. A lot of that, the board is on wax, right? So you have some wax, and then it's in a little tray. Basically, the board is a little tray. It dries, and then you could do some writing. And then if you need to reuse it, you just get rid of the wax and pour some more wax. So there are a variety of media that could be used, yes. Because of course we really do, I made this point early in the talk, we take for granted the presence of pen and paper as a sort of medium, but we should not take it for granted. You know, until the development of the pulp and paper industry, paper is very expensive. We now live in this world where I'm just surrounded by paper. It's everywhere. Many of us live these lives of paper. But that is a very contemporary phenomenon. We should not take that for granted at all.
I mean, of course, as is also this, what do you call it? Conspicuous calculation, the kind of mass numbers, like what is it, the national debt that you talk about?
I do. Yeah. So, you know, in downtown Manhattan, there's this thing called the National Debt Clock. And it's basically this accounting document. It's not a real count. It's this sort of artificial electronic document that's made to impress us all about how much debt America is in. And, you know, I think it obviously serves an ideological purpose as such, related to a particular political orientation. We don't need to adopt that in order to be able to look at that sort of text and say that it's very impressive. What it really is serving is this enormous symbolic function of just emphasizing just how much money it is. And the number doesn't have to be real. The number can be quite artificial, but it serves this purpose of symbolically impressing you with just how large this number is. And actually, for most humans, there's good cognitive evidence that beyond 1,000, human beings are terrible at understanding what numbers really mean. So for instance, if you ask people if you set three numbers in a row or give them three numbers like 1,000, 1,000,000, and 1,000,000,000, and you ask them to kind of relate those to one another, some people will actually just kind of put 1,000,000 halfway between 1,000 and 1,000,000,000. It seems like it, right? It's right there in a kind of nice row. And of course, I'm talking about an American billion here, not the old British. Anyway, you know what I mean. Yeah. And the milliard, we can get into the terminology. But in fact, of course, these are things that really exist in a logarithmic relationship to one another, but are often presented in a more linear fashion. Because beyond a certain point, millions and billions and trillions don't actually mean much to most people. I've done some other work on what I call indefinite hyperbolic numerals. And these are numbers that are in English like the number zillion or squillion. Numbers that in fact don't have any referent at all, really. They're just impossibly large numbers that are sort of used for playful purposes. But in fact, those are playful, but they're also very serious in one sense, that we're using these numbers to indicate that it's so big that, well, you might as well not matter to think about it. You might as well just think about it as an impossibly large number. But in fact, in the number word systems of lots of languages, the biggest common number that's used often also means a lot. And so you think about Greek myrios, which is, myriad, which is sort of 10,000, and it's also a lot. Or in Egyptian, there's the word / God / number, hech, which is 1 million. But it's also sort of infinity or countless or something. So hech is like the God of countlessness, the God of infinity is a very strong word. Infinity is a distinct mathematical concept. But there was certainly this idea of things being uncountably large. And so usually at the top of your number system, you have something that's uncountably large. Well, in English, we've just taken that to the extreme by developing a bunch of words that look like numbers linguistically, and they act like numbers linguistically, but they don't mean anything.
I remember trying to explain to my children when they were little that we don't count rice. Rice is uncountable. And they pulled out the rice and said, sure you do, Daddy. Look, 1, 2, 3, 4, 5.
One rice, 2 rice. Yeah.
That also reminds me, when I was at my previous university back 2003, 2004, 2005, I had a thing on my website which was calculating the cost of the Iraq War. It really freaked the university out. And they said, take that down. They didn't send never, ever directly to me, said, take it down. But they said to my head of department, tell Steve to take that down. And he then never said to me, take it down. And it was, I have no idea whether it was accurate. It was simply a phenomenally large number, which expressed a particular political view I had of the war, of the U.S. occupation invasion of Iraq, which, the number was serving a political purpose, which I think is very much throughout your talk and throughout your book. You do talk about how numbers as representation systems are an entry point into cognition, but also into the politics of a community.
Yeah, absolutely. And we're, in some ways, we're a more numerate society than previous societies. That's certainly, we are surrounded by written numbers to a larger degree. And so, for instance, the Americanist historian Patricia Klein-Cohen set out in the 80s the notion that it was really in the 19th century that Americans became a calculating people, that things like censuses and things like the sort of detailed enumeration of all sorts of phenomena became fundamental. And there really is a large literature in science and technology studies on quantification and the way in which things have come in modern society to be quantifiable. Most of that literature, though, doesn't engage with the kind of things that I'm engaging with. It doesn't engage with old texts, and it doesn't engage with these earlier traditions. And I actually think it's not that, I think that's much to its disadvantage. I think there's a lot to be gained by looking at not just at modern states and what do modern states do, or what do people who are, for instance, drawing from, Foucault, think about numbering. But what do people who are looking at ancient Mesopotamian writing or ancient Egyptian writing, or pre-Islamic or early Islamic Arabic writing? How do we use their numerate practices as part of really a whole suite of thinking about the ways that societies use and think about numbers? And I think that broadly comparative perspective is, it's one of the important things that we as anthropologists can bring to the table to a broad comparative science of quantification or social study of quantification.
Interesting. Okay, we've got another question in the chat box. And I am not an Arabic specialist, so I'm going to say this very badly, but the Rasail al-Ikhwan al-Safa, Treatises of the Brethren of Purity, an 11th century work, has a volume 14 dedicated to maths and has a theory of number to a great degree similar to the Neo-Pythagorean arithmetical theories. And this is from Hussein Jassani. He asked, does anyone know if it talks about the origin of numbers?
So I don't know. That's not my area of expertise, and I think that's. But many of these texts do talk. Having seen some of them and looked at some of them, many of them talk about number systems in this sort of very general way. They're not really talking about origins, except that usually they'll say, well, yes, we know that this, the Arabic numbers come from India. That's really the first, the widespread recognition that's still recognized to this day. But in terms of really a broader discussion of like the origins of numeration, other than that, no. And in fact, even the Indian texts I'm familiar with don't kind of go much further than that. They talk about numbers in a very different way that's outside of a distinct accounting of the chronology of how systems developed or where numbers come from. There's a whole, of course, branch. I mean, you could talk about, both in whether it's in China or in India or in Greece, about the sort of philosophy of mathematics. That's a much broader subject than I would be able to talk about today. I'm not familiar with this particular text, so I don't know the answer to the question as asked.
Okay, thank you. That actually reminds me, I remember some years ago we were talking about counting on your fingers, and I mentioned that my Punjabi friends use the segments of their fingers, which I thought, okay, that makes a base 12, the logical, quote unquote, logical numbering system. But of course, you've been talking about Indian numeral system, and that is a decimal system. So it obviously doesn't follow that people use their fingers as their base system. But in India, they've got this decimal system, and yet the people that I've worked with use the segments of their fingers, and they clearly, 12 is important. 12 is how you get 12 from your segments of your fingers, not 10. So I'm wondering, how come India has a base 10 and contemporary Punjabis use these segments rather than their fingers? That's probably an unfair question, but I'm going to ask it anyway.
No, it's a very good question, but the answer is more complicated than you think, which is, of course, that hands don't only afford a particular one kind of counting. Of course, there's the idea that you're going to count actually on imagining your fingertips and your thumbs. Those, you've got 10. You mentioned segments, and of course, then you could look at the 4 fingers, not counting the thumb, and you could count each segment, and then you would get 12, as you point out. But you don't have to count the segments. You could also count the lines. You could count basically your knuckles, and now you've got 8. And, there are actually numerous ways that you could divide up your hand. The question of even 5, we think in most languages of the world have decimal numerical bases or some multiple of 10. So for instance, 20 or 60. Bases like base 8 and base 12 are pretty rare. A project I'm working on right now is looking at the archives of the Dozenal Society of America. The Dozenal Society is a group that is dedicated to the advocacy for the base 12 numeration as a superior form to base 10 numeration. In fact, it used to be called the Duodecimal Society of America, but then they decided that was too decimal centric and they should change their name to the Dozenal Society. They're a real curious bunch. I kind of love them in that kind of weird way that weird people who like things like this are fun. But it's actually a serious subject because it goes down to questions, for instance, about metrology, right? The division of the foot into 12 inches. And simply the fact that 12 has a lot of divisors. Again, it's one of these highly composite numbers. 10 only has 1, 2, and 5. That's so limited. Whereas if you had 1, 2, 3, 4, 6, and 12, what a beautiful system. And this kind of discourse is very interesting. It's not likely to actually create the change that they want for the reasons I've already talked about, that this is not the way people actually make the decision about what notation system to use. But to return to your point about the fingers, really the question is, for me would be, well, not just how do they divide up the hands, but what are they doing with those? For instance, are they using a metrological system for instance, for weights and measures or for length that actually depends on that. And if that's the case, then I think that makes a lot of sense for them. But we don't want to assume that there is a singular logic to this, that there's only one way you divide up your hand, and that's the obvious way. Because I'm sure it's obvious when they present it to you, you're like, oh yeah, that makes a lot of sense. But of course you could also, why aren't you including the thumb in that? What's wrong with your poor thumb? You know, it's got some knuckles too. I admit it's not much of a finger, but it's very important, you know, in its own way. So those are the sorts of questions that, again, they probably don't motivate people on a day-to-day basis, but that you want to look at hands and fingers. And our colleagues, Andrea Bender and the late Sieghard Beller, have a fantastic paper they published a few years ago outlining the various systems of finger counting worldwide, a really brilliant cross-cultural study.
Well, of course, the thumb is the pointer, so you can't use it in the way they count. But anyway, right. That's a conversation for another time. Tony Christie has another question about zero. So Tony, I've just invited you to unmute.
Yeah. Earlier you mentioned that the first Indian numerals in Spain in the 10th century only have 9 numerals, no zero. And there are other contexts in which there's, again, you have 9 numerals, no zero. And 0 is just a placeholder, I suppose, by the but in the 7th century, use 0 as a number and gives all the rules for calculating with 0. Why didn't the Arabs take over his complete system?
So I'm afraid you were breaking up a little bit, so I didn't hear the entire question.
I just repeat, why Brahmagupta has 0 as a number? Mm-hmm. Why didn't the Arabs take over 0 as a number when they first took over the Hindu number system?
So that's a really interesting question. Part of the reason actually has to do with some very local sort of cosmological features. I mean, in India, this concept of sunya, which is really, I mean, it comes to be used as 0, but it's really like a nothingness or a void, is cosmologically very important. And so when we don't necessarily want to assume that when a notation gets developed, those cosmological features that may be local or maybe specific to either a religious tradition or a certain set of practices don't necessarily come over in the same way. So it's not, so the question is, well, what do you need to know to do what you want to do with something? And so when we look at texts like the Codex Vigilanus, those are tricky because they're really existing almost outside of a lot of the context about how those numbers would have been used. But one other thing to think about is that often in those the early use of Western numerals, they weren't being written on pen and paper either. They were being written on jetons or tokens. And then you could actually just lay them out on a counting board. And if you're doing that, then you don't need a 0 at all. You actually only need the 9 signs because where there's a 0, you just leave a gap. So instead of writing 901, you simply put 9 in the first column, leave a blank, and you put 1 in the third column. So it really also depends on what we know about the material and embodied practices that are underlying a notation. It is very rarely about the notation itself. Whereas with pen and paper arithmetic, we kind of see that necessity to have 0 really being fundamental. So the real question is, there was probably a sort of sense of like 0 that's certainly not absent from the early Western texts. There are some that have it, but it really was seen for the most part as a different sort of thing, as a thing that was not quite a full number. But actually, I think if you ask your average school child today, you'll get actually much the same answer. 0 is a very funny number. It's very, to use the terminology of cognitive anthropology, it's not very prototypical as numbers go. You know, the counting numbers starting with 1 are the most prototypical, and then 0 is pretty weird. Negative numbers are super weird. Irrational numbers, very, very weird. Complex numbers are weird. Transcendental numbers, weird. Transfinite numbers. These things all go out in a long line of weirder and weirder numbers. The cardinals are pretty central because they're present in every human counting system, and 0 is not part of the counting system in languages. We don't count with 0.
Okay, thank you. We've got a question now from Lauren Hayes.
Hi, Steve. This is actually Randy Haas. I'm with Lauren, tuning in
Right,
together.
Randy.
That's okay. Yeah, so I have a quick question. Thanks for a very thought-provoking talk. It made me think a lot about sort of the cultural dimensions of numeric systems, and intersects with one of the problems I like to think about, which is sort of the evolution of inequality in human societies. And, you know, it seems to me that, like, you know, some of the things you were talking about, like nonlinearities and learning processes and sort of cultural understanding and taking the time to understand different systems could be very related to the evolution of inequality in human societies and how we resolve inequality. So initially we might feel like equal taxation systems, for example, might be everyone contributes equally to the system. That's equal. But at some point we recognize that no, maybe there's something else going on there, that maybe a percentile system is more appropriate system of taxation. So in our education system at a very young age, we learn about percentages, and then that helps. But today, you know, I think a lot of conversation about there's still inequality in sort of taxation systems. And so we come up with these sort of like hack systems of tax brackets. And I wonder if there maybe there are some fundamental mathematics that society is missing or unwilling to learn that could be at the sort of the core of debates and tensions in society over sort of what is fair. So I guess I'm sort of curious to hear about your thoughts on, you know, is that a fair characterization? And hear your thoughts about sort of the relationship between the evolution of mathematical systems and inequality in societies. I know that's a huge question, but maybe some initial thoughts. I would be really curious to hear what you think.
It sounds like a great question for us to have over dinner once we can all be together again, and I would really enjoy that. But to give you a very short answer, one that does draw on a different part of the book, one that I wasn't talking about today, but that I've talked about elsewhere, is that it really is important to know that these numerical notation systems, these 5 basic structures, are actually emergent with the development of state societies throughout the world. That you don't see the development of this kind of base structured numerical notation outside of the development of systematic hierarchical social inequality, and you see it alongside the development of writing in Egypt, in Mesopotamia, in China, in lowland Mesoamerica, in highland Mesoamerica, in the Andes. That each of these places has its own notational system that is emerging, maybe not alongside the state, that gets into a complex question of what is the state, but alongside the use of notation and writing for the building and maintenance of systems of social inequality. So that is absolutely the case. Then you come to terms with the fact that all of these systems, the time and energy that it needs to learn them, the time and the energy that it needs to teach them, require, at least to some degree, some form of surplus extraction and then the maintenance of inequality through some form of redistribution. We can sort of leave that as a question to be established empirically. But then it's very clear that these are not happening in equal societies. And it's not to say that egalitarianism and numeracy are opposed to one another, not at all. It's very clear that egalitarian societies are numerate societies, but these particular kinds of notations are an emergent phenomenon that occur alongside the development of particular kinds of pre-modern state societies. And that's actually one of the reasons why I think that the anthropologists are as well or better suited to investigate this than folks who really want to focus on the sort of early modern and modern periods alone. That I think if your theory of the state starts at 1500 or 1600 or 1700 CE, that you've made a mistake because you're not really able to understand the way in which those systems of inequality work. And so David Wengrow's work is really fundamental to my understanding of much of this for people who read that sort of literature. So thanks for your question.
Of course, you also in your book spend some time talking about David Graeber's work on debt and very similarly, how important that historical record is that doesn't include the state. that going back, I think you'd say goes back 5,000 years. So I mean, do you, I think that's a really interesting dinner conversation, but also here, I wonder, is debt part of this numerical representation system? And does the numerical representation system we have now, would you say that we could have the kind of capitalism we have now without these numbers, without this Western numbering system?
Well, you're going to put me on the spot, are you? Well, let me tell you what I think about that. Yes, of course, you're right. And when I talk about Wengrow and Graeber, close collaborators, Graeber, of course, tragically passed away late last year. But his last book, co-authored with Wengrow, is going to be coming out later this year. And it's really, I'm really looking forward to it. It's going to be pretty essential because it really is, both Graeber and Wengrow have as a common understanding the idea that the kinds of inequality that we currently have are not inevitable, that they exist and that they're not eternal. And so even by choosing, you know, Graeber's book is called Debt, the First 5,000 Years. For me, it is not a coincidence that he's using that 5,000 and that I'm talking about numerical notations, which have existed for 5,000 years, because that's where his book starts. It starts with Mesopotamia, and it starts with the kinds of accountings of debt that occur in Mesopotamian states, you know, in city-states such as Uruk or Jumdet Nasr. And so the idea of these yes, recording of debt is important, but where I would really want to qualify it is the understanding that it's the calculating of the debt may actually not need the numbers, but it's the recording of the debt, the serving as a mnemonic, that's actually fundamental to understand. You can't have a long-term debt without some sort of information storage system for managing that, and for some sort of communication system so that it's not just being stored in someone's memory about how much that you owe. And so, yeah, it's absolutely fundamental. Now, the question is always how much is the economic system linked to numerical system? And I actually think that in some cases, it's not clear. So for instance, I've talked elsewhere, not so much in Reckonings, but in other publications about the fact that, you know, if you look at the lowland Mesoamerica, you look at the Maya and the sort of the Olmec and the sets of notations that are there, Maya inscriptions aren't about the economy. You never have somebody writing, oh, we took 2 million sesterces of tribute when we killed these people. All of their numbers are about the management of time, and it's the management of the calendar. They simply don't record quantities of goods, quantities of people, quantities of debt in the same way. So that leaves you with two options. The first is to say, well, they simply weren't doing that at all. They weren't using notation to manage debt. Or secondly, you could say, well, maybe they were doing it, but those were in all those codices that got destroyed. That's tragic, but then that presents us with a real empirical problem. We don't like to argue from no evidence that they must have been doing it just because they did it in Mesopotamia. I think that's a bad argument. I think we should leave some space to acknowledge that actually maybe there are other ways to manage this other than with notation. Because I think that if they were spending a lot of time writing about the economy, somewhere that would have ended up in a big monumental inscription. Somewhere they're going to talk about the number of prisoners killed or the number of bags of cacao. But there's very, very little in Mesoamerican textual tradition, in lowland Mesoamerica, that would indicate that that's true. Among the Aztecs, it's quite different. The highland Mesoamericans are constantly recording tribute. We think of Aztec and Maya, I think we shouldn't, but sometimes those kind of get conflated together and like, oh, you know, highland Mesoamerica, lowland Mesoamerica, it's all Mexico, or it's, you know, but that's really quite wrong. That's not a correct understanding at all. That these are different language families. There is borrowing between them, but in many ways, like, you have to think of them the way you would think about, you know, ancient Egypt and ancient Mesopotamia. But those are very, very different regions of the world with very, very different writing traditions and very, very different purposes to what they're doing.
Thank you. So I've got a question from Khurshid Sana Khan. I'm going to ask you, Khurshid, to unmute yourself, if I could find your name here. Where are you? There you are. Okay, I'll ask you to unmute yourself, and you can ask a question about numerological calculation used by Arabs.
Hi to everyone. Thank you very much for your very interesting presentation. My question is for Professor Professor Stephen, and it's about HVSAB Jamal. I'm just wondering how, if Arabs were using, and I assume that they still use this calculation to know about the fortune. I'm just wondering, what is the origin of that? This from paganism, because now all Arab countries are Muslim. So if they are still using, does it has to do anything with the paganism? Thank you very much.
So thank you for your question. I don't think it has to do with pre-Islamic beliefs, except in the sense that I do think it has to do with some of that tradition absolutely is related to that whole set of what I've called ciphered additive systems. They're alphabetic systems that are used not only in Greek, but in Hebrew and in Arabic. And all of these have alongside them traditions of numerology in which those numbers are being used for finding symbolic connections or for making those sorts of calculations. So in the sense that Arabic societies and Islamic societies more generally are part of that sort of broader and Eastern Mediterranean tradition, yes, they're all derived from very, very old sets of practices that continue on to the present day. And so you see the idea of the gematria, which is a sort of Hebrew number magic. I'm mischaracterizing that. That's not quite fair. But it's one of the ways in which these systems are really useful because each letter has a numerical value. This affords you to make a connection between, for instance, the letters of a name and some number, or to go the other way, to take a date, some date, and then to encode it in what's called a chronogram. In other words, to basically take the numbers of that date and then to turn that into a word and make a connection between the number and the word. This is extraordinarily useful. And I want to absolutely, one of the reasons I didn't want to stress that today is that I didn't want to overly mystify the Arab world. And I didn't want to engage in that kind of crass Orientalism that sometimes you see, which is like, oh, look at those people in the ancient Middle East engaged in this mystical thing. It's not that they don't do it. It's actually that I'm actually much more interested in looking at an Arabic astrolabe and saying, look at these really smart people doing science that I honestly could never do. And they're using a number system that has been characterized as primitive or as awkward or whatever, but in fact, it is nothing of the sort. So it's not that this isn't relevant. I just didn't want to stress it out of a desire to not overly mystify the arithmetic that's going on in the Islamic world, much of which is actually pretty understandable to us.
Thank you, Steve. Okay, we've got a comment here. I think it's an interesting one. It goes back to some of the things you were talking about earlier with sexagesimal systems or decimal systems. Mm-hmm. So the comment comes from Alzbeta Somolayova, that the Indo-Arabic system was, of course, not the earliest place value number system. Correct. The Babylonians had one, but it was a sexagesimal system that base 60, and mathematically, a base 60 system is, in some senses, superior to a base 10 one. This is the comment. The Babylonian system also initially suffered from the fact that it possessed no zero. So this Babylonian sexagesimal system is the reason why we have 60 minutes an hour, 66 in a seconds, 60 minutes in a degree, and so forth. So the question is, can you tell us a little bit more about this base 12, this kind of 360? I mean, you mentioned it a little bit, but I guess part of the question is, if this was a kind of computationally effective, productive system, why do you think this one just dropped? Why do you think this wasn't the one that kind of clung forward and survived?
Okay, so that's a big one. So first, thank you for your question. And I talk about place value sexagesimal notation extensively in my earlier book, the big numerical notation book, which unfortunately is pretty expensive these days, but I still think it's well worth a read if anyone's interested in it. But yeah, it is clear, and that's as early as around 2000 BCE or 2100 BCE, Babylonians were taking an additive system and turning it into what I called in one of my slides, a cumulative positional system. In other words, it uses the repetition of signs, but within each power of the base up to 60. But then for each power of 60, it sort of exists in a sort of place value system. So in one sense, I mean, the reason that sexagesimal base 60 notation is useful for some purposes has to do with the very reasons I was raising to do with Tony Christie's question earlier, that 60 is highly composite and 360 is highly composite. It lets you divide things up much more easily. And that's why, especially if we're doing fractions and doing division, it's pretty useful to have. Having said that, the notation that was used, one of the reasons that you don't use it is it's a cuneiform system that does use a lot of repetition of signs, but it's also not clear that you don't need that notation to do sexagesimal arithmetic. Modern astronomers do sexagesimal arithmetic all the time. They're using base 10 numbers. They're using decimal place value numbers in the same way that we would say, 6 hours, 22 minutes, 31 seconds. Now, we don't often think of, the fact that it's 2:48 and 29 seconds as a representation of a number, but it's a representation of a period of time in a base 60 system. But the system is base 60, but the notation is base 10. That's the key difference there. But it's also clear that when most of us do that kind of arithmetic, we're not really using numbers at all, or not in the way we often think. A problem I often present to students, because my anthropology students often don't like arithmetic, is to ask them a question. Say, it's just a simple question. How long is it from 10:30 to 11:10? And they'll think, and usually they get it pretty fast, and they say 40 minutes. And I say, okay, how did you get that? And then they'll say, okay, well, I started at 10:30, and then I went up to 11 o'clock, and then I went another 10 minutes past that. But then I say, well, see what you did there. You are actually using the clock as an embodied artifact. You're basically using clock arithmetic. But it's not, I don't have to see a 6 there and then go up to the 12 and calculate that all by 5. I don't sit there and go, well, I go from 6 to 12, and that's 6, and 6 times 5 is 30, and then I add another 2 times 5, which is 10. No, I actually just go and I'm like, oh, that one's half an hour, and then another 10 minutes on top of that. And so I'm actually using the hands of the clock more than I am any particular numerical system to do that computation. What's actually interesting is if you talk to younger people, people really who are in their teens, they're actually not very good at clock arithmetic the way that we do it, or that I would do it at least. And part of the reason is that they mostly have learned to calculate digitally, and they mostly are exposed to digital clocks rather than analog clocks. All of which is to say that, yes, this is absolutely, there are questions about why we would use one system rather than another, but you always have to come down to the question of, well, how are they doing the actual calculation? We see how they did the representation, but how did they do the calculation? And, there really are open questions about whether there is a connection between the Babylonian 0, and which did eventually get a 0, and Indian 0. I don't think so. I think these are really quite separate, in the same way that I think the Mesoamerican 0, the Maya 0, is really clearly its own thing. There's not some person sailing across the Pacific or the Atlantic to tell the Maya about 0. But what's really important is to understand the social and the cosmological systems in which those zeros exist, and those are not necessarily simple. So with regard to the Mesopotamian case, Xiaoli Ouyang at Fudan University has been doing a lot of fantastic work on the very, very earliest Babylonian place value inscriptions. So not the stuff that we're most familiar with, which is much, much later, mostly first millennium BCE. That's where the bulk of the texts come from. But these really, they're late third millennium, 2100 BCE texts that have the very earliest evidence of place value, that kind of get at the question of where did that come from? How did we get the first place value? And that sort of stuff is really fascinating to me.
Thank you. It is, I agree, it is fascinating. It makes me think about the possibility, since your book is so much about cognition and numbers as a representation of cognitive systems, or at least cultural systems that are cognitively stored and produced, it makes me think about the numbers that the people that I work with use, the numbers for surface area of land. So, you know, they have a canal as the base unit of, or the most common unit of land measurement, which is 1/8 of an acre. They talk about monde, which is a weight, a volume of 40 kilos. And I wonder, I mean, I simply don't know enough information about it, but I wonder if they might simultaneously be holding a kind of a series of base 12 kind of categories in their head that they're expressing, that they can also quite easily calculate using decimal system. Because when I ask them, what is a monde, they can very easily tell me what that is in kilos. They don't have any trouble, but I'm not sure they're thinking of it in kilos. They're thinking of it as a monde. Monde is their 40 kilo thing. They don't need to do the translation. They have it both sitting in their head. Do you think that there's any way to test something like that?
So sure, absolutely. And I think you could test it with the folks you're working with, and there is some ethnographic work on that kind of thing. But you could also, you know, there's really, really good evidence, both sort of anecdotal, but I think also some empirical evidence about the way that, for instance, anyone who's very skilled in a kitchen works with units of measure. So metrology, or the study of weights and measures, intersects with numbering, but in a kind of complicated way. And one of the things about weights and measures is, yes, we live in a, you know, other than in America, in a very metric world. But there are real advantages to having a system where there's a lot of binary divisions, because a lot of what you need to do when you're cooking is halving and doubling, right? If you want to know, okay, well, I have 4 cups and I want to know, all right, how many pints is that? Or, you know, that these are the sorts of things that are actual practical arithmetic that you actually need to solve. And halving and doubling are really essential to that. And having things with lots of divisors, whether that's 8 or whether that's 12, actually serves a very useful purpose there. Whereas when you're just counting objects, then probably base 10 has that value. So this is a different, you see this all over the place. So for instance, the Roman numerals we're all familiar with, I talked about today, but Roman fractions are base 12. And so there's division into 12 uncia, which is actually like ounce. It's the same word basically, and it's the same as inch. So these are all the same, and that's because dividing metrology sometimes requires a different set of practices that have to do with fractions. It's really unfortunate. At present, there really is no good comparative history of fractions. And some people are trying to get me to write one, but I'm afraid I don't know if I have enough time for it. But it's really desperately needed. There are a couple of little books and a couple of accounts that are decent, but fractions are really what are linked to metrology. It's really about how you divide up the land, right? And this is a problem that occurs. If you're like, how do I divide up my land among my 4, the 4 people who are going to inherit my wealth? How do I do that? Or how do I divide up? These are calculations that are very different than the question of, about rates of debt accumulation, where I think a decimal system with decimals rather than fractions is perfectly fine for calculating compound interest over 20 years. It's probably very useful to have a long set of decimal places that extends out, as your debt accumulates and accumulates and accumulates.
Thank you so much, Steve. We're at 7:56 where I am in my time zone, which means by my reckoning, we have only 4 minutes left for that hard stop. So I have now enabled everyone to unmute themselves at will. So if you would like to all unmute yourselves, and we can give Steve a round of applause to simulate something like being in the same room, I think that would be a fantastic way to finish off. And Steve, it remains for me to say thank you so much.
Thank you. Thank you.
Wonderful.
Yeah, we're getting lots of comments here saying thank you for an interesting talk, splendid talk, and I do think this is the kind of talk that Aga Khan University's Institute for the Study of Muslim Civilizations really does welcome. I think this is absolutely the kind of bringing together of history, of culture, of cognition, all of that, which can be so fascinating, but also so difficult to do. And I think the talk you gave was stimulating, engaging, but it comes out of a book that I really do think is a must read. I mean, I have rarely read many books on numbers that, well, just full stop. I've never read many numbers many books on numbers, but this one really is full of the kind of juicy stories that keep you going from page after page. So Steve, thank you so much. And best of luck with your next book on fractions, which I will also read with eager interest.
Thank you. Thank you, everybody. And thank you to those who've stayed now the full 2 hours of this discussion. I was quite surprised to see how long it's been, but it's been a wonderful, wonderful discussion. And please feel free to write me with any further questions, or follow me on Twitter, or buy my book. That would be a great choice that you could make.
Okay, thank you. We will have more events in AKU ISMC. For the time being, they will all be online. So if you think this Zoom thing worked, then do write to our communications team and tell them to do more Zoom stuff, because we're always playing with how to do this kind of live event. We want to replicate as much as possible the in-person event. So without further ado, I would say thank you all to the audience for your critical engagement. Thank you, Steve, again for a wonderful talk, and have a good evening. Bye.